Now, good. So now we have everything, right? We learned the basics. Now, again, I say you don't need to memorize any equation. You need to understand the reason behind, because this is not a class just for MOSFET. You are going to apply this intuition to all the novel device. If you don't have this intuition, it will be a big pain for you because you need to rederive every time for every new device. Now, something called CV curve. What is CV? Anyone know? What does CV stand for?
Capacitance voltage.
Thank you. Capacitance voltage curve. So what does it mean? If I have a transistor, N plus P, I am going to apply a voltage bias. And I ground this part. I'm going to switch from -5 volts to +5 volts. And then at the same time, measure capacitance. Okay, and at the same time, I will measure the capacitance. So how is it going to look like? Now we know that it's not simple. Right? As I said, I'm going to switch the VG from negative voltage to positive voltage. Am I going to measure the capacitance of the gate, right? If it is a simple capacitor, we know it is just equal to capacitance of the oxide, but we just learned that, oh no, that is complicated. On the left, when you have a negative bias, can you remind me again, what type of mode is that? Accumulation, inversion, depletion? For this figure? Accumulation, thank you. And then what is this?
Depletion.
Depletion. And then inversion, right? Again, let's remind, what happened to accumulation? When I apply negative VG on the left, I accumulate a lot of hole here. So effectively, this is a conductive plate. So what capacitance do I get? It's just the capacitance due to the oxide, right? Because whenever I change the voltage a little bit, all the charge will go here. Remember what is capacitance? It's just dQ dV. I change the voltage a little bit, I measure how much more charge will go in. And since this charge, you see that they are only separating by the oxide thickness. So I expect that I will get Cox. In this region for accumulation. Okay? Makes sense, right? Because you just look at this one. This is the charge you put on the two sides of the metal. It just looks like I have two sides of the oxide. It just looks like I have a oxide as the insulator, and that is the capacitance. But when you start going into depletion region, what happens? When I change the bias, on the top, yeah, I add charge, but at the bottom, I actually add the charge to the depletion region, right? This part is changing. So effectively, I actually have a thicker insulator. And it keeps increase when I increase the gate voltage. Okay? But eventually, when I reach the threshold voltage, what happens? Now, when I increase the gate bias, I'm increasing this one because this one is fixed. The depletion region is fixed. When I increase the voltage, I add more electron to here. So for the whole system, it looks like I still just have a capacitor separating the charge by Tox. So this one will go up. And this is the inversion. Right? Is that clear? But if you understand what we talked about before, then this probably is much clearer. But the problem is you need to recognize the meaning of capacitor. Again, you solve Poisson equation, you do all the math, you get exactly what I give you here. But now we try to understand this as what's the meaning of a capacitor. Capacitor is just this, dq dv. Please remember this. You measure a capacitor by just like a water pond, right? A reservoir. How you know whether this is a big or small reservoir? You pour some water into it, Q, and you look how the water level change. Well, if the water level change very fast, you think, wow, that's not a big capacitor for water, right? Because it may be very narrow. That's why you pour a little bit water, then the level goes up. If you keep pouring water into the reservoir, the water level goes up, and assume there's no leakage. You will say, wow, this is really a big capacitor, correct? And that's what we do, dq dv. And of course, then you solve Poisson equation, that is just equal to the distance you put the positive and negative charge. When it's accumulation, you put it just right next to the two sides of the oxide, epsilon over T ox. When you go into depletion, the charge are put one side of the oxide, but the other side. Okay, I realized my internet was not stable, right? But that's okay. The main point is I try to say that for the accumulation, right? You put the charge just to the two sides of the oxide, right? So it is the capacitance of oxide. When you in depletion, you put the one side of the oxide, but the other side of the depletion region, it is thicker. A thicker, effective thicker insulator give you smaller capacitance. That's why you keep going back. Until when you reach inversion, boom, it comes up. Is that okay? Any questions?
Yeah, can you explain what does exactly comes down? Is it a depletion width or is it a capacitance? What is it going down from the accumulation part, from that part,
yeah,
all the way to inversion? What is that going down exactly?
Right. So what is going down is the capacitance. Okay. But why the capacitance is going down? Because capacitance is related to how far you put the two opposite charge. When it is in depletion will keep increasing. So you will start putting the charge further and further away from each other. That's why it goes down. It's just as if you have a thicker insulating layer.
So if the depletion width keeps increasing, the capacitance goes down, and if the depletion width reduces, the capacitance goes up. Is that the relationship between them?
The depletion rates keep going up, and then your capacitance keep going down. If your depletion width reduce, then your capacitance will go up. Until a point, and in inversion, your depletion width doesn't change anymore, but it's irrelevant anymore because the charge you are going to put is here instead of here. So now the system only see this isolation, this distance. So that's why it goes back to C ox.
Okay, got it. Thank you, Professor.
Okay, good. Why this is important? Because later we're going to use this to, again, apply to other devices, okay? Now, so if you cannot take everything home today, right, for this slide, right? First, you recognize the curve is like this. Second, recognize the meaning of capacitor. The meaning of capacitor is you put a charge and how much the voltage will change. And this really depends on how far you put the positive and negative charge. Okay? But you always put positive and negative charge. If your system is such that the positive and negative charge are very close to each other, then you have a large capacitance. If they are far away, then you have a small one. That is the main point. Okay. Again, you can solve Poisson equation, but that takes a long time. Let's understand from this way. Any questions?
Professor, what is that distance xi on the inversion?
Xi, you mean from here to here?
No, it's the inversion chart. It's little xi distance. It looks like where it begins to invert.
Oh, okay, okay. So I did not pay attention to this. This is just the depletion width. This one is just the depletion width. It's just saying that this is the width of the depletion. But you can ignore this one. It try to tell you that in this situation, I have the depletion of this. Not really depletion. This is just telling the distance when the Fermi level hits the EI. I will suggest you to ignore this one. This is just another quantity, but we don't need that. It's just when the Fermi level equal to EI, the distance. But the depletion width is more than that, yeah.
Okay.
Mm-hmm. Okay, now, so we learned about the CV curve, right? Now I want to ask you, what happens if I have fixed charge? So this is V, this is VG, we know very well. Okay, I draw the CV curve, then it goes up, inversion, right? Now, what if I have a positive fixed charge? Meaning that this is the gate. So again, my connection has problem. My question is, this is the regular CV curve, right? Now, what if I have some negative fixed charge here? Meaning I have some charge here. Negative, positive, or negative fixed charge. Do you know what will happen to this curve? Any idea?
Channel.
You shift left and right.
Yeah, shift left or right, yes. So if I have a positive charge, is it going to shift left or right? Now think about, I just told you, it is going to change the threshold voltage, right? Remember? VTH becomes VTH minus QF divided by Cox. So if I have positive with fixed charge, what will happen to the curve? Shift left or right? It will shift left. Right? Because this is just negative QF divided by Cox. So this is for positive. Right? Again, as I said, right, this is just, we just discussed this. We say that when we include this fixed charge, we just have a constant shift of the threshold voltage. And it is the same for everything else because it just changed the initial condition of your system. Okay? What if I have a negative fixed charge? What will happen? Shift left or right? Anyone? If I have negative charge, then QF is negative, so it's negative minus negative, right? So it's going to shift right. Any questions?
Yeah, what determines these positive and negative charges on those equations?
Charge I give you, you are given. I already tell you that what if I have positive charge? And that depends on your transistor.
That's the only thing that you will tell us if it's a positive charge, or will you give us a number, dimension?
Yeah,
something?
in the test, in the exam, in the assignment, it's going to be given you the value or whatever. You don't need to determine whether it's positive, negative. But I can give you two curves and ask you whether it's positive or negative.
Oh, okay.
Right? I give you the green curve. I ask you what is the fixed charge there. How do you explain the shift? Right? I say, okay, theoretically, I expect to get the red, but in the experiment, I do the measurement, I get the green. How do you explain it? Can you say, oh, maybe there is negative fixed charge?
Negative charge.
Yeah. Okay.
Where's the threshold voltage?
Threshold voltage is this one, right? When you go to inversion, these are the threshold voltage. Right, just refer back to these figures. It go to inversion here, right? So this is the threshold voltage. So I try to stop here. I think you guys got a lot of stuff already, but I will stay. Let me know you have question. We can have Q&A. Yeah, please feel free to leave if you need to leave. Any questions?
I had a question on traps.
Yeah.
So in the project that I'm working on, they make a lot of mention of traps and how it changes the acceptor traps change the threshold voltage. They make it more negative.
Mm-hmm.
Could you explain that again and how that works?
Oh, I have not covered the trap yet, so I will cover it next time. Here it is only fixed charge, so you see that it got shifted parallelly. But if you have the interface trap, then it is going to distort your curve. But I will cover it next time.
Okay.
Yeah. Charge capacitance. That's why we have this red line. Is that okay? Any questions? Now, and then we say, what if I have some fixed charge between the oxide and semiconductor? Then we just follow the equation. We remember that the threshold voltage becomes the original one minus QF divided by Cox. So you have a positive charge, you just shift everything to the left. If you have negative charge, you shift everything parallel to the right. You either try to understand or memorize it. You have no choice. You need to know how to draw it for this class, right? But it's okay if you don't completely understand, but that may make you difficult to solve more difficult problems, right? Any question about this shifting? Now, if not, what if it is interface trap instead of interface charge? Now it becomes very complicated. Let me still draw the curve, right? For the ideal one. This is VG. This is C. The ideal one is like this. Accumulation, depletion, suddenly inversion. This is ideal. Now in my transistor, unluckily, this is the gate oxide. There are some traps in between the silicon and the silicon dioxide. If I try to draw the band diagram, maybe I should draw this first. I'm showing you something. Can someone tell me what is this mode? Inversion, depletion, or accumulation?
Accumulation.
Accumulation. What is the voltage at the gate? Negative or positive?
Negative.
Negative bias.
Thank you. Because it pushed up, correct? When we say we have trap, what does it mean? Remember that this is the band gap. Inside band gap, there is no state. There should be no electron. But because at the interface, due to imperfection, you actually have some state that can have electrons. Okay? And let me tell you, for example, let's say This is acceptor trap. Okay. Now you tell me, is this acceptor trap empty or filled?
Assuming that is above the EF, it should be empty.
Empty. Why do you say assume?
Because you drew the EG instead of the EF.
Okay, very good. So EG, what I'm talking about is just this is EG. This is actually EF. This 9 is EF, but I'm trying to say this is the gap. So now is it empty or filled? Just use your reasoning. Is it empty or filled?
Empty.
Huh? Say again.
It should be empty.
Empty. Because it's above the Fermi level, right? So what is the charge when acceptor is empty? Maybe you forgot, right? Try to think about that. Now I show you the table again.
Neutral.
Neutral, right? Acceptor, empty, neutral. So if it is neutral, is it going to affect my curve? If it is neutral, it's just as if it is not there, correct? You don't have charge, you're neutral. Yeah, the state is there, but it's not affecting anything. So when you draw the curve, they're just exactly the same. Okay? But now, let me look at a more higher voltage. Someone tell me, is this positive or negative gate bias?
Positive.
Positive. Now this might be in depletion or accumulation, but doesn't matter. The point is, the trap is still there. Now can you tell me, are the trap filled or empty?
Filled.
Someone say filled. Are they all filled?
50%.
Thank you. Those at the bottom are filled. Those on the top are empty. If you are empty, you are neutral. You have no effect. I can ignore you. Those are filled. Are they what? Negative or positive bias?
Negative.
Negative. I mean, charge, not bias. Negative charge, right? So then it means that if this is just equivalent to have negative fixed charge. We already learned that what happens if you have negative fixed charge? What happened to the curve? It shifts to the right, correct? So it means that when you go to a high bias, you actually shift this guy to here. But it has to be continuous. So this one is going to run in this way. So it's not parallel shift, right? It's a distorted shape. Right? Not parallel. So indeed, this is one of the methods for people to figure out whether you have fixed charge or trap in the interface. Measure the CV curve by looking at the shift compared to ideal case or theoretical case. You know that what type of trap it is. Now I only give you acceptor. I don't have time to go to donor. You can do the same thing. For donor, you're going to distort to the left. Is that okay? Any questions? Now, besides this, there's also one more important feature. In reality, you will see the CV to become larger in some portion because you have the capacitance due to the trap capacitance. Right? A little bit difficult to explain, but how do we explain it? When your Fermi level, when EF crosses the trap, it needs to fill the trap, correct? When you cross it, you need to fill it. That is just equivalent to have extra capacitance. Because you need to put extra charge in order to increase the gate voltage. So if you have trap, you also will see a bump. And this bump will tell you where is the trap level. For example, in this case, it's very uniform. Then you will see shift everywhere. But if your trap is concentrated to only a certain region, right? Now let me do that so that you won't get control. Right. Let me say I only have trap in this region. Right? Then you will see this bump. Okay? Now if you can draw this curve, we did not talk about any equation, no theory here. It's all intuition, right? Understanding of physics. If you can draw this, then you understand CV curve. You understand a lot of device physics. If not, please try to understand. And I challenge you to draw it for donor case at home, right? If you cannot get it right, let's discuss together. Any questions? I feel that it's very difficult to read for you. Okay. So that's what we want to talk about CV curve, but very important. Although it's so simple, two terminal, but it gives a lot of information regarding the capacitor and also the interface quality. And we are going to use this for ferroelectric and also other more complicated stuff. Any questions? Is that all clear? All clear? You can ask anytime, right? If you have question.